So what I want to do is to begin with giving you some perspective on what a limit is, because that's the topic that we're going to be working on this whole chapter, and it helps, I think, to have some good notion, going in as to what it is that we're talking about. So let's suppose that I have a function, and um, and here's my function. Suppose f of x is x squared plus 2x minus 3 over x plus 3. Well, never mind. Hold on, let's change it. Let's do over x minus 1. Okay. Let's suppose I want to figure out what is f of 1. Okay. If I try to plug 1 into this function, in the numerator, 1 squared plus 2 times 1 minus 3 over, in the denominator, 1 minus 1. 1 squared is 1, plus 2 is 3, minus 3 is 0. 1 minus 1 is 0. And we should all, hopefully, at this point realize that if you divide by 0, something bad happens. Okay? Mathematically, we say that what you have is not a number, but in the greater context of life, what you have is, and this is just, I don't know why it works this way, but every time somebody divides by 0, somewhere in the world a puppy dies, and it's terrible. So we don't want to ever do that. Okay, so I can't plug 1 into this function, at least not safely, for the sake of puppies. So f of 1 doesn't work. So, we could say that, f of 1 is undefined, or we could say that f of 1 is not a number. Okay, so that's no good. What about x values close to 1? Can I plug in something close to x equals 1, like x equals 0.5 or x equals 0.9? Those would work fine, right? Anything except 1 in the denominator is going to give me, a perfectly non-zero number, so I won't have to worry about dividing by 0. Okay, so I can plug in other things, right? I could say, like, all right, what is f of 2, right? We could compute that. 2 squared plus 2 times 2 minus 3 over 2 minus 1, right? So we'll get 4 plus 4 is 8, minus 3 is 5, over 1 gives me 5. Oh, okay, that's nice. All right. 2 isn't that close to 1, but it's, sort of in the same general vicinity. Maybe something really close, like f of 1.1. Okay, and maybe I want my calculator to help me out here, because I don't want to do 1.1 squared. So I take 1.1 squared plus 2 times 1.1 minus 3, and we get 0.41. And then if I take 1.1 minus 1, I'll get 0.1, and when I divide, I get 4.1. Okay. If I try something even closer, f of 1.001. Okay. I plug that in my calculator, and I will get 4.001. All right. Well, these are all numbers that are bigger than 1. What if I try something smaller than 1? What if I try like f of 0.5? Okay, so that's 0.5 squared plus 2 times 0.5 minus 3, and 0.5 minus 1 in the denominator. Okay, so I get negative 1.75 in the numerator and a negative 0.5 in the denominator. And when I divide that, I get 3.5. Okay, Let's try even closer to 1. F of 0.999. Turns out that I'll get 3.999. Okay, well, that's interesting. Do I see a pattern here, right? It looks like when I'm getting closer and closer to 1, 5, 4.1, 4.001, closer from the other direction, 3.5, 3.999, it looks like we're getting closer and closer to 4. So it looks like for x near 1, f of x should be near 4. Okay. And we have a mathematical way to describe that. We can say, well, as my x values approach 1, the y values, or f of x values, approach 4. Okay. In math, we like to replace as many words as possible with symbols. So instead of saying approaches, we'll just use a little arrow. So a way that I could represent this a little more mathy is as x, and I'll use an arrow to signify approaches 1, and f of x, arrow 4, right? Approaches 4. Okay. So that's sort of describing what's going on here. All right. Before we talk about limits, I want to keep looking at the same example and look at this as a graph. Okay, so let me pull up my graphing calculator, and I'm going to go through and graph this function and look at what happens when we get close to 1. Okay, so my calculator, I'll put in the function, right? This was x squared plus 2x minus 3. And then divided by x minus 1. When I graph it, it looks like a line. It looks like I can plug anything I want into here, right? The line looks just normal, right? It doesn't look like I have a problem at 1 at all. I can even zoom in a little bit. I'll zoom in. Oops. Close to where x is equal to 1. Zoom in a lot. Looks fine here, right? Trace along the graph. My trace is being weird. What's going on? Let's try this again. Okay, I'm just setting up my graph window here. Okay. It keeps, oh, I have a stat plot on. I have a stat plot on. It's messing things up. That's what's causing issues. Okay. Now I trace along the graph. Oops, I didn't include my 1. I'm going to go from 0.9 to 1.1. Okay, so we're super close to 3 here. And now that I've zoomed in super close, it almost looks like I have a little piece missing in my graph. If I trace along, everything's going fine, and then when I hit 1 exactly, it gives me a blank for the y. Okay. And the problem is my calculator has the same problem I do. When you plug 1 in, you don't get a number out. And when I have it normally zoomed, you can't really see that, but if I zoom it just right, sometimes I can see that little gap missing. Okay. So what's going on here is that if I were to look at this function and try to simplify it, right? So my function x squared plus 2x minus 3 over x minus 1, I could simplify this a little bit by factoring the numerator. Right? If I factor the numerator, I'm going to get an x plus 3 times x minus 1. Okay. And x minus 1 in the numerator, x minus 1 in the denominator, it feels like I want to cancel those. And we can, as long as x is not equal to 1. And this is where we have to be careful. This is where it's important when we're working with functions to keep in mind our domain. In my original function, 1 is not defined. I can cancel these terms and write this as x plus 3 with the provision that x is not allowed to be 1. Okay, because when x is 1, here I get a 4, but here I don't. That's why when I plug in things near 1, I can say, oh, I'm going to be near 4, because I'm just going to take my x value and add 3. And that's the same as what I have over here, except that when I plug 1 in exactly, here I don't get a number, and here I would get a 4. So they're not exactly the same. This is an important thing to keep in mind. All right. Now, in math, what we're going to do is we're going to say, well, I want to be able to talk about this. I want to be able to cancel these and not worry about that 1 in the denominator. So let's just talk about what happens when I get super, super close to x equals 1. This idea of approaching. And that's what the idea of a limit is. Okay? So the limit as x approaches 1 of f of x equals 4 means that when x approaches 1, then f of x approaches 4. Okay, so that's what this limit means. It means that as your x values get super, super close to 1, your y values will get super close to 4. Okay, when we're working with a limit, because we're talking about approaching 1, we're not actually looking at x equals 1 at all. Right, when we're plugging in values back here, we don't actually plug 1 in. We started with that and we saw that didn't work. So we said, what happens when we go nearby? So it's important to note that when we're working with a limit, we ignore what happens exactly at x equals 1. So the limit is only looking at x values nearby. Okay, that's an important thing to keep in mind. That's what makes the limit useful. If I wanted to plug x equals 1 in exactly, I don't need any of this new notation. I could just plug 1 into the function and be done with it. Okay. I don't want to exactly repeat what you're going to be going through in the lecture videos, so I'm not going to. I just want to emphasize some of the important points. So I'm not going to follow everything that the lecture videos do, and that's not to say that like that's not important or it doesn't mean anything. Okay, you need to go through that. I'm not trying to replace that, is what I'm saying. What I want to do is emphasize some of the important points. Okay, and what we did back here with plugging in values is something that we do a little bit in section 2.1. This isn't a very effective method for finding limits, though. It's really, really cumbersome, takes a long time, and it may not be accurate because it relies on me seeing a pattern. And in this case, the pattern was pretty clear, but in other cases, the pattern may not be. Okay. Yeah, so this is a good point, right? If dividing by 0 worked, then, 5 equals 7, right? 1 equals 2. I heard this great proof once. If 1 equals 2, then I am the Pope, because the Pope and I are two people. 2 equals 1, so Pope and I are 1. Right? So that's, I don't know. It's an old clever little exercise for why we have to be careful about things where we end up with 1 equals 2 or 5 equals 7. Okay. So yeah, dividing by 0 ruins everything, right? It doesn't work, and it doesn't make sense. So when we're working with a limit, we're only looking at what happens as we get infinitely close. We're not looking at what happens exactly at that number. And that's why in this function, I can look at a limit as x approaches 1, but I can't plug 1 in exactly. Okay. So having said that, now we're going to do something kind of weird. I'm going to skip forward a little bit, and what I want to do is talk about the beginning of section 2.3. Because in 2.3, it seems like we're going to just start plugging in 1, and that's weird. I just said that you can't. Okay, here's how 2.3 works. We're going to start by establishing some general rules, right? So what I want to do is look at the limit as x approaches any number, some unknown number a, okay? And I want to start with something really simple. We'll just look at 1. And what I mean by that is, let's suppose I have the graph of y equals 1. And I want to say, all right, let's suppose x approaches 4. What's y approaching? Well, y is always 1, so it's approaching 1. What happens if I approach 2? Well, y is approaching 1 because it's always 1. What if I approach some unknown number a? Well, y is still always 1, so it's going to be approaching 1. Okay. So this limit is equal to 1. It doesn't matter what value we approach here. And in fact, we can generalize this a little bit, and this is going to start to look a bit abstract. But let's suppose that I have some constant c, and I look at the limit as x approaches a of that constant c. Well, I don't know what c is, but y equals c is just a straight horizontal line. And any x value that you pick, if the y value is always c, then we're going to be approaching c. Okay, this is our first limit law. All right. Let's make a slightly more complicated function. Let's look at the limit as x approaches a of the function x. So I'm going to look at a graph of y equals x. If y equals x, then if, I say, what happens as I approach 2? Well, if I pick x values close to 2, then the y values are close to 2, right? If I picked -1, if the x values are close to -1, then the y values are close to -1, because the x and y's always match. So if x is approaching a, then the y values will approach a. And so that's the value of the limit. That's our second limit law. Okay, now there's two different categories that limit laws fall into. One is finding the limits of certain functions, which is what we did here. And then there's combining together functions, which is what we're going to do next. So now I'm going to look at what happens as I take the limit as x approaches a of two functions added together. Okay, and let me just give you an example over to the side. Let's suppose that f of x is 2x plus 1, and let's suppose that g of x is, we'll say, 5 over x. Okay, and I want to find the limit as x approaches, say, 3. Okay. Of f of x plus g of x. Okay. Well, if I add these two functions together, f of x plus g of x is equal to 2x plus 1 plus 5 over x. So I could plug things into my formula, 2x plus 1 plus 5 over x, and see what the pattern is, right? So we can make like a little xy chart like we did a minute ago and say, all right, let me try 2.9, and I'll plug into that. Here, I'll get out my calculator. I'm going to cheat a little bit. I'm going to plug that formula in as a y equals. Okay. And then I'm going to, on my main screen, hit variables, go over to y variables, function y1, and I'm just going to use function notation. So when I plug 2.9 in, it'll do the computation for me, and I get 8.52. Okay. So now let's try that again. Let's get even closer to 3. Let's try 2.999. And I get 8.6665. Okay, let's try what happens if I'm slightly bigger than 3. What happens if I plug in 3.0001? I get almost the same thing, right? To the number of, you know, 3 to 3 decimal places is the same. The 4th decimal place changes a little bit. We get 8.666. What was that? 8. Okay. All right, maybe I have to get a little bit closer just to be sure of what's going on. Let's go 2.9999. Oh, I missed one of my 9s up here. 9999999. Okay. Well, now I got a lot more 6s going on. So 2.9999999. Oops. And I get 8 point, and I get 6 6s and then a 5. Okay. I put some more zeros here. So 6 zeros and then a 1, then I get 8 point and a bunch of 6s. Okay. And I think we got an 8. All right. So I think that we can see a pattern here. It looks like as x approaches 3, it looks like we're approaching 8.6 repeating. So I'm gonna guess that that's what that is, right? So the limit as x approaches 3 of f of x plus g of x looks like it's going to be 8.6 repeating. Okay, let's look at another way to do the same problem. What if instead I look at the limit as x approaches 3 of f of x and the limit as x approaches 3 of g of x separately? Okay, so for f of x, I'm just looking at 2x plus 1. So if I plug in 2.999, let's get this ready for later. Okay, so now I put 2x plus 1 as my function y2. Okay, if I put in 2.999, I get 6.998. If I put in 3.001, right, 7 and change, it looks like I'm approaching 7. 2, yeah. So it looks like the limit as x approaches 3 of f of x is just a straight up 7. Okay, that one looks pretty straightforward. The other one I think is where we're going to run into some problems, right? That 5 over x bit is where I get a bunch of decimals. Okay. And if I put in 2.999, here I put 5 over 5. 5 over x in as y3. So variables function go down to y3. If I put in 2.999, right, I can see, oh, there's where some of those 6's come out. If I use more 9's, I get more 6's. Okay. If I put in a number a little bit bigger than 3, all right, same idea. It looks like I'm going to get about 1.6 repeating. All right, so we're not going to write down all of these values. We can just say, all right, I think that the limit as x approaches 3 of g of x is 1.6 repeating. Okay, now notice what happens. If I take 7 and I add it to 1.6 repeating, I get 8.6 repeating. So if I'm taking a limit where I have two functions added, instead of plugging all these numbers into one, the combination, I could plug them all into one function, plug them all into the other, and then add the results. Or vice versa, right? So our first limit law is that if I'm adding two functions and taking a limit, it's going to be the same as doing those two processes separately. I can take the limit of the first function, the limit of the second function, and just add them together. Okay. So that's a limit law. And we get a bunch of limit laws like this. And I'm not going to go through and demonstrate with an example like this for each one of them. And I don't think that your book is either, but the idea works the same, right? I could also subtract functions, and it works the same way. The subtraction of two functions I could break up as two different limits, and I would end up with the same result. Okay, so that shouldn't be too much of a surprise. But we can do more than just adding and subtracting. We can also get into things that start to look a little bit different. If I take a constant multiple times a function, I can factor that constant out. And the way to think about this one is if I'm looking at a function and I'm always multiplying by the same number. Let's suppose it's 8. Take a function and I'm always multiplying by 8. Then if I just didn't multiply by 8, all of my number patterns would be, a factor of 8 less. Okay, I could just multiply the end result by 8 and I'd be in the same spot. Okay. The next one is kind of building on that same idea. Instead of multiplying a constant in a function, I can multiply two functions. And that's the same as if I multiply one function and figure out what the limit is, and then multiply the other function and then figure out what the limit is. Okay. This works for dividing too, but dividing is a little bit tricky. So if I take f of x over g of x, the limit ignores what happens exactly at a. So if I plug in a number that makes g 0, if a is a number that makes g 0, that's okay in the limit, but it's not okay outside of the limit. So this is going to be the same as plugging into f and plugging into g separately, except that if this limit is 0, that doesn't work here on the right, but it could here on the left. Okay, so provided the limit as x approaches a of g of x is not 0. All right, and we're going to explore that one here in a minute. All right, if I can multiply functions, I could multiply the same function by itself, and that would just be f squared. So this process also works for exponents. And this will be the last one that I write down. But if I take a function and I raise it to a power, I could have instead figured out the limit of that function and taken the end result to that power, and I'd get to the same thing. Okay, so for a start, these are our limit laws. Here's the thing about the limit laws. I don't really want you to use the limit laws directly when you're doing homework problems. Okay, and this can be confusing because the videos will go through limit laws too, and it's easy to get lost in all of these laws, right, and this big process. So what I want to do is show you how do we put these together in a meaningful way. Okay. So let's look at an example. Find the limit as x approaches 3 of x squared plus 2x minus 7. Okay, here's what I'm going to do. Instead of plugging in a bunch of numbers near 3, I'm going to use the limit laws. Right. So here's my first limit law. I know that if I'm adding two functions, I can break it up over addition. Well, I could do that twice and break it up over 3 additions, right? So using that first limit law, I could say that this is the same as the limit as x approaches 3 of x squared plus the limit as x approaches 3 of 2x plus the limit as x approaches 3 of negative 7. Okay. And then I can use my constant multiples limit law to factor out a constant multiple out of the second one. I can use this last limit law with exponents to bring the limit inside for the squared. Okay, so I could write this as a limit as x approaches 3 of x squared plus 2 times the limit as x approaches 3 of x plus the limit as x approaches 3 of negative 7. And then I can actually compute these limits directly because we started off by saying if you're taking a limit of just x, the limit as x approaches a is just a. So you can just replace that limit with the number a. And if you're taking the limit of a constant, you can just replace that whole limit with just the constant. So this limit inside here, x approaches 3 of x, I'm just going to get 3. The limit as x approaches 3 of x, same thing, I'm just going to get 3. And when I take the limit of a constant, I just get that constant back. Okay, now I could do the arithmetic here, right? 3 squared is 9, plus 6 minus 7 will give me 8. But the thing that I want you to notice is that when I finish my limit laws, what this looks like is exactly the same as if I just plugged into my original function. Okay, so this looks exactly the same as just plugging in f of 3. So when we're computing limits, we can sort of put this together as a rule, right? And we actually call this a theorem. Okay, and I don't think that the theorem is necessarily called this, but I'm going to label it as this so I can refer back to it. But this is what we call direct substitution. Okay, here's how the theorem works. If I take the limit as x approaches a of f of x, that's just equal to f of a. I can just plug into the function to figure out what the limit is. And this only works for certain functions. Okay, now based on what I did here, if I have any polynomial, I'll always be able to break a polynomial up over its additions. I'll be able to factor out the constants. I'll be able to bring the powers out. And so I'll be able to break any polynomial down into all of its pieces. Okay, so the list of functions that I can work with here includes polynomials. Okay, one of my limit laws also said that I can divide functions provided I don't have a 0 in the denominator. So we're going to say this works for polynomials. This also works for fraction functions, or what are called rational functions. Okay, as long as we don't get a 0 in the denominator. Okay. In later sections, we'll find out that this also works for trig functions. This works for exponential and log functions. Okay, this works for basically all the functions we work with as long as we don't end up with something undefined. Okay. Now that's not exactly true, and we're going to explore that in a little bit more detail when we talk about continuity, right? And that's when we'll find out when does it not work, right? But the reason I want to point this out is because this idea of direct substitution, we can always try, and that's how we're going to compute limits. So when you're going to compute limits, you're never going to use the limit laws directly. What you're going to do is you're going to use direct substitution. Okay, so let me show you a couple examples. So first, let's find the limit as x approaches 4 of, let's say, 8x to the 10th minus 5x squared plus 3. And the way that I would figure this out is I would say, all right, this is a polynomial. I can do direct substitution. So I'm just going to plug in 4 for x. Okay. And I'll use my calculator to compute that. So we get 8 times 4 to the 10th minus 5 times 4 squared. Plus 3. I get some crazy number. 8,388,531. Okay, and the number isn't important, but the idea is that I can solve this just by plugging in direct substitution. This is how I'm going to do the limit. Okay, done. All right, let's look at another example. Let's take the limit as x approaches 4 of x squared plus 2x minus 3 over x minus 1. Okay, what I'm going to do is try direct substitution. And as long as I don't get a 0 in the denominator, then I'm okay, right? So 4 squared is 16, okay, plus 8 minus 3. 4 minus 1 is 3, and I get 7. Okay, so we're done. All right, now let's look at an example. Limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. Here, if I try to plug in, I end up with 0 over 0. And what that means is I wasn't actually allowed to plug in. So this is not equal to the limit. Okay. If you end up with a 0 over 0, or if you end up with any 0 in the denominator, you weren't allowed to do direct substitution. Now, that doesn't mean that this limit doesn't exist. What it means is that you can't use direct substitution here. And this is where limits get really tricky. And this is where I think it's very easy to get confused, because I can't use direct substitution on this function. Okay, but I can still do algebra stuff. So I can say, all right, I have this limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. And we looked at this same function earlier, and we said, okay, I know that I can factor that numerator. And the numerator factors into x plus 3 times x minus 1. The denominator is just a factor of x minus 1. And earlier, what we said is, if I cancel these x minus 1s, I have to be careful because x is not allowed to be 1. But we already have that condition, because when we look at a limit, we're looking at x values infinitely close to 1, but we're not looking at 1 exactly. So it turns out that, yes, I can indeed cancel these, and this is equal to the limit as x approaches 1 of x plus 3. And on this limit, I am allowed to use direct substitution. So I can't use direct substitution with the limit we started with. But I can with this one. And here, if I plug in 1, right, and I get 4, and I follow my chain of equality, so we can say, so the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1 is just equal to 4. Okay, now, if you look at this and you're like, this doesn't feel right. It feels like I'm doing some sort of weird trick where I'm saying you're not allowed to plug in 1, and then I plug in 1 anyway. And what's the deal, right? And if it doesn't sit well with you, I almost take that as a good sign, right? That means that you're trying to understand things, and that's good, and it seems confusing, and it should, because this is the key to what makes calculus work. And calculus is not a simple idea. It's an idea that we can all learn, but, you know, it was geniuses that came up with this, right? Like Isaac Newton, and he didn't do it on his own, right? I think there's this great quote from Isaac Newton: "If I have seen further than other men, it is because I stood on the shoulder of giants," right? And that's really true. He didn't come up with this stuff out of nowhere. There was a lot of buildup. His advisor Barrow had a lot of connections to almost getting things exactly right here. He set things up, but couldn't quite make a connection. And now we can talk about history of math another time. But the idea is that this idea of a limit is weird. But what we're trying to do is get around this idea of dividing by 0. And that's going to help us deal with infinity. And that's really what limits are all about, trying to deal with infinity and deal with these problem areas and for functions. Okay. And by doing that, we can open up a whole big chunk of math, being able to solve problems that you can't solve otherwise. Okay. When we go through and work out limits, starting in 2.3 and then for the rest of your life in calculus, we don't ever use the limit laws like I did in this example. Okay, we don't break them up one limit law at a time. So the idea is to talk about the limit laws so this makes sense, but when we go to solve problems, we want to be using direct substitution. Okay, because that's really putting all the limit laws together. That's what makes direct substitution work. But for solving problems, that makes a lot more sense, right? You plug in. The reason we're allowed to plug in is because of the limit laws. Okay. Does this make some sense? All right. So that's the main thing that I wanted to get through here today. So when we go to solve problems, especially in 2.3, you'll have a lot of them where you do this factor and cancel bit to solve a limit. What I want to do now is maybe just touch on one more complicated concept that we run into in these first few sections of Chapter 2, and that's limits that involve infinity. All right, what I'm going to do is I'm going to start by looking at a graph of a function. So this is the graph of y equals 1 over x. And if I try to plug in x values close to 0, I'm going to run into a problem. You can see with 1 over x, I obviously can't plug in 0. But if I plug in something close to 0, I'm going to get a really big number. Okay. Here's a way to think about it. Just doing some quick mental math. If I plug in 1/10, 1 divided by 1/10 is 10. Okay, so if I plug in 1/10, I'll get 10. If I plug in 1/100th, I'll get 100. If I plug in 1/1000th, I'll get 1,000,000,000. So you can see the closer I get to 0, the closer that reciprocal will be to infinity. And you can see that on the graph too. All right, so when I look at this function, I don't really get a value that I'm getting closer and closer to, right? My numbers are getting further apart, so it doesn't really seem like the limit is going to work here. Okay. But we can still sort of talk about what's going on to the function, right? It's going up higher and higher, and we can think about it approaching, instead of a number, I can think about it approaching infinity. Okay. Let me draw another graph of a different function over here. This function is going to look very similar. A little bit careful. So this is y equals 1 over x squared. And I do get different numbers out when I squared, but the main thing the square does is it gets rid of negatives. So for my first function, if I plug in negative 1/10 into the reciprocal, I'll get a negative 10. But here, when I plug in, I'm always going to get a positive, right? I don't get 10 out when I plug in a 10th. I'll get 100. But the idea is that it's going to be positive. So we can talk about what's happening to the function. Here, the function is going towards infinity on both sides of 0. So what we can do is we write the limit as x approaches 0 of 1 over x squared is equal to infinity. And the only way that we can really do that is with the understanding that infinity is not a number. So really, the limit as x equals 0 of 1 over x squared isn't a number. So it doesn't exist. However, it's more useful to write equals infinity because that describes what's happening with the graph. So we're going to write the limit as x approaches 0 of 1 over x squared equals infinity because it's useful. Okay, and because you understand that infinity is not a number. Okay. Over on this side, the problem is that I can't write infinity because it's approaching infinity on one side and negative infinity on the other. Okay, so here, on this example, we write the limit as x approaches 0, 1 over x, does not exist. So I'm going to write DNE for does not exist. Okay. So this is the idea of infinite limits. We can still write a limit as equal to infinity or equal to negative infinity if that's the direction that graph is heading as we approach it. But we might still get a not exists if the infinities don't line up. Okay. And the way that we can check that is we can look at what are called one-sided limits. So I can look at the limit as x approaches 0, and if I put a little positive where a power would normally go, right, as a superscript, then that indicates that we're approaching from the right. Okay, and in that case, if I'm only looking at approaching from the right, then my graph is definitely approaching infinity. Okay, likewise, if I look at the limit as x approaches 0, and I put a little negative here, that indicates that we're approaching from the left. And my function is 1 over x. Then I'll have a negative infinity. Okay, so one way to think about limits, if I have like infinite limits, or if I have like a piecewise defined function, which you might see sometimes, for the limit to exist, I have to approach the same number on both sides. Okay, so you can think about it as the limit from the left and the right have to match. Okay, so if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x, then the limit exists, right? So if both of those match, and let's suppose they're equal to something, I guess we'll just call it L, then the limit as x approaches a of f of x is equal to L. Okay, so the left and right limits, if they match, then the limit exists, and if they don't match, then the limit does not exist. So if the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x, then the limit as x approaches a without any left-right on it does not exist. All right, everything I talked about today, again, the idea is these are things that I think that you could benefit from hearing twice because they're confusing, right? So going from the concept of limits to actually computing limits where we don't really use the limit laws, it's just baked into direct substitution, and then moving on to infinite limits and this whole idea of, limits from the left and the right, are all things that I think that you really should you could benefit from hearing twice, and that's why I'm saying this now. So in theory, all of you should have already looked at the lecture videos. If you haven't, you still need to look at all the lecture videos. I did not cover everything that needs covering in these sections. But hopefully by giving you a second exposure to this, or maybe this is the first time, right? Maybe it's not in chronological order, that's okay. But by getting 2 exposures to this, hopefully that will really cut down on the amount of confusion, and you'll have a better time going through the material and the homework. Okay, so we'll still have a homework review as Monday's class. The difference is that on Monday we're going to be in person. Okay, so we'll go through some homework problems when we meet in class on campus, and that should be good times. Get some questions answered. On Monday in class, we're also going to have a quiz. I will post an announcement on Blackboard tomorrow detailing exactly what's going to be on that quiz, because we haven't had any quizzes yet because we've been remote. But our first quiz should not be, it won't be anything crazy. It's going to look exactly like some of the homework problems, okay? And I'll give you a lot of guidance on exactly what to expect, right? So the first one will be very, very straightforward. But that's what we're looking at going forward. Any questions right now? Okay, if you have any questions, that you want to ask, or if there's any, maybe a homework problem or something, anything you want to do, just go ahead and stick around.